Hello everyone, and welcome to the video teaching lesson for the online math course 171 on chapter 2 section 1. We're beginning a new chapter here, chapter 2, about solving equations, the primary topic of the chapter, and solving inequalities. And once again, you see on the screen here the best I can do in writing with my fingertip on the iPad. It's that's just how it comes across, but at least I'm able to do this with you, so at least it's a way to communicate. So yeah, the chapter title is Solving Equations and Inequalities, and we're going to do all the sections in this chapter except the very last section. We're not going to do section 2.7. I don't know what happened here. Something's going on. Oh no, just lost that screen. Let's see if we can get it back. But what I'm saying is we're going to talk about the first just pull that up. We're going to talk about the first 6 sections of this chapter, and I've got this up on the screen now. I don't know what, apparently the air server that allows me to use the iPad is malfunctioning again, which that's certainly less than ideal, but this happens sometimes. But we're going to talk about the first 6 sections in chapter 2, all about the first 5 sections all about equations, and the 6th section about inequalities. We're not going to do 2.7 about linear models and scatter plots. That's just not intended to be covered right now in this course. So this teaching lesson today is about the 2.1 section in the text. So I'm going to have to improvise here now, because I was planning on going over this with you using the iPad and demonstrating some problems, but it looks like I'm going to be limited to being able to talk with you verbally and point out things here in the text and use some examples in the text. So let's go ahead with this. Let's talk about what an equation is and the different types of equations to begin with. An equation is a mathematical statement saying that 2 quantities are equal to each other. So you've got one quantity, you've got another quantity, and whenever we put an equal sign in between them, that tells the reader that the statement is being made that those 2 quantities have the same value. They are equal in value to each other. In amount, they're equal to each other. And they may have variables in them or not. We're of course only interested in equations that do have variables in them. So it's really, when I say mathematical statement, it's very much like drawing upon English vocabulary. It's very much like a mathematical sentence. Saying this quantity equals that quantity in math symbols in an equation is really a math sentence. And later on, when we get to section 2.6 about inequalities, and we say this particular quantity is less than that quantity or greater than or equal to that quantity, that once again still is a mathematical complete sentence. It's a complete thought, just of a different nature. So usually what we're concerned about with equations is we're wanting to know what values of x will make that equation true. And we call those values of x the solutions of the equation. The solutions of the equation itself are the values of the variable that make the equation, or in the case of an inequality, make the inequality to be true, to be a true statement. And there's 3 types of equations. The main type of equation that you and I are interested in is the kind of equation where the variable can only take on maybe 1 or 2 or 3 or a limited set of values. And that's what's known as a conditional equation, as they show here right on the first page of section 2.1, page 160 in your text. A conditional equation is an equation that's true for certain values of the variable, but not true for other values. Generally, it's true for only, like I said, one or two or a few values of the variable, and there's by far most values of the variable do not work. That's your typical conditional equation, so-called. It's a technical term, but that's the kind of equations you and I are used to working with. For instance, if we say 2x plus 3 equals 5, simple little linear equation, as we call it, because if you graph that, if you graph it with, instead of, if you put like another variable in there and make it into a line with a y, you of course have a linear graph, but it's linear in the sense also that the x is only to the first power. So when we say 2x plus 3 equals 5, that equation is only true, for instance, if x equals 1. So 2 times 1 plus 3, 2 plus 3, yes, that's 5. Any other value of x other than 1 will not make the equation 2x plus 1 equals 2x plus 3 equals 5, will not make it true. The other two types of equations we'll just briefly mention here. The identity equation is unusual in that that type of equation is true for every real number in the domain of the variable. If, for instance, I gave you the equation 2x plus 2x equals 4x, obviously very, very simple. 2x plus 2x equals 4x, that's true for all values of x. Whether x is 0, x is a negative number, x is a positive number, it can be a whole number, a decimal, an irrational number, anything, but is whatever x happens to be, the equation 2x plus 2x equals 4x is obviously going to be true for every value of x. So that's an example of an identity equation. The contradiction equation is one that no matter what value you put in for x, the equation is still going to be false. And the simplest example I can think of a contradiction where it looks like it's an equation, but it's actually false, it's not true, it's really not equal on both sides, is, for example, if I made the claim x equals x plus 1. Find all values of x such that x equals x plus 1. And no matter how hard we try, of course, we will never find any number which can be substituted in for x to make the so-called equation x equals x plus 1 to be a true statement, because no number can equal itself plus 1. So that trying to write that out as an equation is it's almost a misnomer. It is a contradiction. It is a false equation in that sense. All right, so like I said, we're going to be dealing with, throughout this chapter, what we call conditional equations that do have solutions, limited number of solutions, but they do have solutions. Now, what we're going to do together in this lesson is go over a couple of mechanical steps and methods for solving linear equations where x is only to the first power and it's the only variable in the equation, just one variable, single variable, and only to the first power, no x squared or x to the third, no square roots of x or anything like that, just x to the first power. So that's what we mean by a linear equation in x. We're going to review a couple techniques for solving couple specific kinds of linear equations, particularly those involving fractions. And then we're going to review some formulas and a couple types of word problems that are important kinds of problems that are part of this course. So first of all, a linear equation that has fractions in it. And I was going to go over some of these with you with the iPad, but the computer system today is not going to let me do that. So we'll use example 1 in the text on page 160, where it asks us to solve x over 3 plus 3x over 4 equals 2. And let me just suggest, when you and I see an equation like this, it's generally not obvious for us just to glance at that equation and say, oh yeah, x is such and such, it's this much. Just the fact that fractions are involved really slows us down in just quickly grasping exactly what number that needs to be. So we do want a very useful, practical, hopefully simple method of solving such an equation of this, and I'm going to suggest there is a fairly simple way. Makes use of a principle that we all learned way back in elementary school, that whenever we have to add two fractions together, the key that allows us to add or subtract two fractions is that they both have the same denominator. And if they do not have the same denominator, then we have to find, if you recall, what we call a common denominator. And in this equation here, there's actually two fractions. We call these algebraic fractions because both the fractions have a variable in them. X over 3 is one fraction, 3x over 4 is the other. And so these two fractions have two different denominators, 3 and 4. So the first thing we need to do is figure out what is the common denominator, and then I'm going to suggest to you something. Instead of the technique that you and I probably learned sometime previous in a previous math course, convert all the fractions so they have the same denominator, we're going to just jump right over that step. Once we find the common denominator, here's what we're going to do. We're actually going to multiply both sides of the equation, every single part and piece, every term of the equation on both sides of the equal sign, times the lowest common denominator. And I trust you recall that whenever you have an equation, not only can you add or subtract the same number from both sides of the equation, but you can also multiply both sides of the equation or divide both sides of the equation by the same number, as long as you are not trying to divide by 0 or even multiply by 0, but anything else. So we can multiply both sides of the equation by the lowest common denominator, and then a really nice, useful thing happens. So let's look at this. First of all, the two denominators, 3 and 4. 3 and 4 have no common factors with each other, so we simply multiply them together to find what we call the lowest common denominator, or LCD, as it's sometimes known. LCD for lowest common denominator, not for liquid crystal display in this case, but yes, so 12 is our number, and we're going to multiply the entire equation by 12, which as a practical matter means multiplying all three terms of the equation, the 2 on the left side and the 1 on the right side, by 12. And when we multiply then 12 times x over 3 and 12 times 3x over 4 and 12 times 2 on the right side, actually, you probably recall this too, when we multiply 12 times x over 3, for instance, we really want to put the 12 over 1, and I was going to demonstrate this with the iPad, but we can't today, unfortunately. But 12 over 1 times x over 3. Now here is the nice part. Since we're multiplying every term by the common denominator, that means all the denominators are factors of the common denominator, 12 in this case. So the 12 and the 3 reduce in just such a nice way that the 3 is canceled out, becomes a 1. So the 12 over the 1, the 12 and 3 have the common factor of 3, so they both, when we divide them both by 3, the 12 comes down to a 4, and the 3, of course, comes down to 1. So that first term becomes, instead of 12 times x over 3, it becomes just 4x over 1, and anything over 1, of course, is itself. So we have 4x. And then 12 over 1 times 3x over 4. The 12 on the top and the 4 on the bottom reduce to 3 over 1. And then 3 times 3x is 9x over 1. And 9x over 1 is just 9x. And of course, on the right side, 12 times 2, you don't even have any fractions. That's just 24. So here's the beauty of this, class. Now we have a fraction all of a sudden, we have an equation all of a sudden with no fractions. 4x plus 9x equals 24. Much, much simpler to work with. So, standard techniques of solving an equation: combine the like terms, get 13x equals 24, and then we don't care how much 13x is, we want to know how much 1x is, so we divide both sides by the number in front of x, if you recall, called the coefficient of x, but the number in front of x, in this case 13, and it turns out that x by itself equals 24/13. X equals 24/13. That is the answer for this. That is a fraction that cannot be reduced. So 24/13 is the final answer. And of course, we could check our answer by inputting 24/13 into the original equation with x over 3 and 3x over 4. Plug in 24/13 in for x. And if we did that, this would prove itself to be an actual equation. For instance, if we go ahead and do that, 24/13 over x, over 3, 24/13 divided by 3 would be the same as 24/13 divided by 3 over 1, so that's just like 8/13. And then 3 times 24/13 over 4. Well, again, 24/13 times 3 is 72/13, and 72 divided by 4 is 18. So we have 18/13 here, and this was 8/13, so we have 8/13 plus 18/13, and 8 and 18 makes 26, so these two fractions together would be 26/13, and that nicely reduces 26 over 13, as 26 is 2/13. It comes down to 2 equals 2. Nothing significant about the number 2, but the fact is that when we plug in our answer in for x, then we end up with a true statement that a number equals itself, and that proves that our solution truly is a solution to this equation, because it makes a true statement when we plug it in for x. Okay. So I highly recommend this technique for solving equations with fractions. Even if you have the x variable in the denominator and have to multiply the whole equation by some expression having x in it, we still actually do that. But as you perhaps are aware, anytime we multiply or divide an equation by any expression that has the variable itself in it, then we have a chance of either introducing some bogus solutions, what look like solutions, what the text calls extraneous solutions, or we have the opportunity, for instance, if we're dividing by an expression with a variable in it, we could actually eliminate an actual solution and not even realize it's there. So we do have to be careful with this. Let's look at an example of what I'm talking about now. Yeah, right here on the top of the next page, they actually do go through what I just went through with you. Here it is, checking that previous problem. Now, extraneous solution, which you see in bold right there, that's the next point I want to address. Oftentimes, if we have an equation that has fractions embedded into the equation, and we have the variable in the denominator of at least one of the fractions, then when we find the lowest common denominator of all the fractions, it's going to have a variable in it. And that means when we multiply the equation by the expression with that variable in there, there is a good chance, not necessarily, but a good chance we're going to introduce what algebraically appear to come out as solutions of the equation, but they really are not, because we've multiplied the equation by the variable, and that caused some bogus solutions to show up. So here's an example of one of these. We'll have to use the example in the text since the iPad is still out of commission. I'm checking and Air Server is still not working. So we'll use example 2 in the text. Solve. 1 over x minus 2 equals 3 over x plus 2 minus 6x over x squared minus 4. At first glance, it looks like a fairly complicated equation with 3 different denominators. It turns out those 3 denominators are actually closely related, though, because the x minus 2 and the x plus 2 denominators, if we multiply each of those times the other, of course, we get exactly x squared minus 4. So that means the lowest common denominator is x squared minus 4, which is, of course, x plus 2 times x minus 2. So when we multiply each term by this LCD, it comes out to something pretty nice. As you can see right here in the text, the first term, 1 over x minus 2 on the left side of the equation, multiplying that times x plus 2 times x minus 2, and I would also prefer to put that over 1 times the 1 over x minus 2. The x minus 2 on the bottom and the x minus 2 are going to cancel from bottom to top, leaving only 1 times x plus 2, which is x plus 2 on the left side. Then on the right, we have 2 terms, the first being 3 over x plus 2, and we multiply that term times x plus 2 and times x minus 2, both those over 1. So the x plus 2 on the bottom and the x plus 2 on the top cancel out now, leaving 3 times x minus 2 over 1. And we can drop the over 1. So it's 3 times parentheses x minus 2. Then minus the third term in the equation, 6x over x squared minus 4, times the x plus 2 and times the x minus 2 factors of the LCD, put those over 1. Then x squared minus 4 on the bottom cancels out with both these parentheses on the top because they're the same, and we're left with just 6x. So we now have, this is so nice, from a rather complicated equation, it's simplified down to just a simple equation with no fractions. X plus 2 equals 3 times parentheses x minus 2 minus 6x. And they have a little footnote over here that x cannot equal plus or minus 2. Where did that come from? That came from the fact that our original equation, that's the one that we're trying to solve, that's the one that counts, x could not be either 2 or negative 2, because if x is either 2 or negative 2, in either case, it's going to make the denominator, 2 of the denominators to be 0. And if you try to divide by 0, of course, it makes the entire expression undefined. So x cannot be 2 and x cannot be negative 2, but watch what happens as we follow through with good, standard, legitimate algebra steps and try to solve this equation now, which no longer has any fractions. X plus 2 equals 3 times x minus 2 minus 6x. Well, let's multiply out the 3 times the x minus 2 parentheses, using the distributive property as it's called, leaves 3x minus 6 on the right, and minus the 6x also. Still x plus 2 on the left. Now, let's combine some like terms here. If we, for instance, from the right, if we subtract, well, if we just subtract 3x from both sides of the equation and add 6x to both sides of the equation, that's going to cancel out both the x terms on the right side of the equation. And from the x already on the left side, we're going to subtract 3x and add 6x. So subtracting 3 brings it down to negative 2x, and adding 6 brings it up to what they show, 4x on the left. And then subtracting negative 2 from both sides, canceling out the plus 2 on the left side. And on the right, negative 6 minus 2 leaves us negative 8 on the right. Almost there. 4x now equaling negative 8, supposedly. And based on the algebra steps. And then divide both sides by the number in front of x by the 4. And that leaves x equals negative 2. Now, before we go any farther, I want to point out neither the text nor we ourselves have made any algebra errors. We have not made a mistake. We haven't missed a sign or done anything incorrect, but we've arrived at a problem. Our solution supposedly is now determined to be, apparently, that x equals -2. But we have already checked and discovered that in our original equation as given to us here with the 3 fractions in it, x cannot be -2. For instance, both fractions on the right side of the equation, if x were to equal -2, both the denominators would be 0. The 3 over x plus 2, plugging in -2 for x, makes -2 plus 2. The denominator is 0. And on the right one here, -2 in for x and squaring it, so -2 times -2 is +4, and 4 minus 4, of course, is 0. So 6x over 0 is undefined, 3 over 0 is undefined. The irony of this, class, is that x is supposedly one of only 2 values out of an infinite number of possible values that x cannot be. Like I say, that's the irony, but it's the fact. So, even though x equals -2 appears algebraically to be arrived at as being a solution, it is not a solution. And what this tells us, since that's the only number we got that x can be, and we already know that x cannot be that number, therefore the answer is, for this equation, no solution. No solution. So that's an example with an extraneous solution where you multiply both sides of the equation by some expression containing a variable and then follow all the correct algebra steps through and see how much x is, but then you have to come back in and plug that value for x back in the equation to see if it works. It's not unusual, class, that when you do an equation like this, you wind up with 2 or 3 or even 4 more values for x. And here's the catch. If you did multiply or divide the equation by a variable expression, you have to check every single one of those possible solutions to see if it's a legitimate solution, a real solution, or is it an extraneous solution that only appears to be a solution. And for instance, if you get 4 solutions, you may find that 1 or 2 or 3 of them are extraneous and the other ones are okay. So it doesn't mean that they're all going to be of one type extraneous or all of the other type legitimate. You can have part and part. And there's no way to know until you check every single one individually. Now, moving forward, I want to refresh the class on some common formulas that everybody has seen before at some point or other in a geometry class or some sort of class. Common formulas that are used in real life to help us figure perimeters and areas and volumes and circumferences and various different things. And I'm not going to go over all these with you right now, but the text gives you all these on page 164. You'll also find some of this kind of stuff on the inside covers of your textbook. But here it is on page 164. These are some common formulas right here. And down below this are other formulas that you may need on some of the homework problems in this section or in this chapter. Some common formulas about temperature, F equals 9/5 C plus 32. Simple interest, I equals PRT. You've perhaps seen that one before. Compound interest, a little bit more involved. A equals P, the principal, times 1 plus little r over little n, that whole parentheses to the n times t power, and explain what all those variables stand for there. And the distance formula, this is a key formula that oftentimes will unlock a word problem for us. D equals RT. In other words, distance equals rate times time. D equals RT. So, now, using these formulas, let's see, okay. Here's an example of using these formulas to solve a problem. A rectangular family room is twice as long as it is wide, and its perimeter is 84 feet. Find the dimensions of the family room. And the dimensions in this case is find the length of the rectangle and the width of the rectangle. Well, what do we know? It's twice as long as it is wide. So we have to pick some variables here. If we let W equals width, L equals length, then we know the length is twice as long as the width, so it is true and factual to say that L equals 2W. We also know the perimeter is 84, and you may recall that the perimeter of any rectangle is just 2 times the length plus 2 times the width, in other words, 2L plus 2W. Well, I was wanting to show you this on the iPad, and I'm going to make one more attempt to see if I can get this back here. Okay, it looks like it's willing to come back. Let's see if, it looked like it was coming back, but let me see if I can actually get it to show now. Well, all right. Maybe we have it here. Let's try this. It's not giving me the option for mirroring. Let's see. Looks like we can get this back though. Okay, yes. Don't need that, wherever that came from. All right. And yeah, here we go. Looks like it is working once again. Good news. Okay, let's take a formula and transform it. For instance, if you had the formula P equals 2L plus 2W, you're going to have some homework problems like this where you're asked to take a standard formula like this, perimeter equals 2 times the length plus 2 times the width, and restate it in terms of another variable. Like solve that formula, say, for L. How much is L equal in terms of P and W? So here we go. To get L by itself, let's subtract 2W from both sides. So P minus 2W equals 2L. I'm very thankful this software is working once again. And now to get L by itself, all we have to do is divide by 2. So the 2's cancel. I'm going to move the L over to the left side now. So the length of any rectangle then is equal to its perimeter minus 2 times the width all over 2. There's a new formula you perhaps have never seen in that format. We simply did some algebra and algebraic manipulation, if you will, to the standard rectangle perimeter formula P equals 2L plus 2W and solved it for L. So now we're having a statement that the length of any rectangle is simply equal to its perimeter minus twice the width, all that, over 2. So you're going to be doing some things like that in some of your homework problems. And Okay, move that on up. Let's do another problem. Say you were trying to find the height of a tree, and it's a sunny day out in your yard, and this tree is casting a shadow and the shadow of the tree is, say, 40 feet long. You use a single mark for feet. And then also in the yard there's let's say there is a bird bath, and it's casting a shadow that is only let's see, it's casting it's casting a shadow that's just 4 feet long, and you happen to know that the bird bath is 6 feet tall. And the question, of course, is what's the height of the tree? Well, what we can do is set up a proportion here. It's probably the easiest way to do this, that the height of either of these things to the length of their shadow is going to be equal to the height of the other one over the length of its shadow. So the bird bath, for instance, is 6 feet tall with a 4-foot shadow. The height of the tree we don't know, we'll just call it H, with its 40-foot shadow. So once again, our proportion is set up that we have the height of the object on the top of either of these fractions divided by the length of its shadow. So 6 feet is to 4 feet for the bird bath, as the height of the tree is to the length of its shadow, 40 feet. And of course, this whole proportion being true is predicated on the fact that the sun casting the shadows is at the same angle in the sky to both the tree and to the bird bath, so that their shadows are going to have the same proportion to their actual height. Well, standard technique of solving a proportion is to cross multiply. So if we do 6 times 40, then that's got to equal 4 times H. So 240 has to equal 4 times H. Divide both sides by 4. Many of you are seeing where this was going already with such simple numbers. So this tells us that the height of the tree is 60 feet. And I've actually, in classes before, had students measure the height of things they couldn't get up to, like how tall is this math building, or how tall is something other, based on doing similar things like this, measuring shadows or measuring angles. And you can actually do stuff like this for real. If you've ever wondered how tall is that tree out in your backyard, you can do stuff like this and actually figure it out. It's pretty neat. So this is more than just a mental exercise. It's actually useful. So that's one type of problem we can do that involves a linear equation. We set up this equation that 6 over 4 equals H over 40, and solve for the variable H. So that's an example of the skills of this section in the text, section 2.1. But let's do one where we're talking about speeds. Let's use the D equals RT formula. Do a problem a little bit more involved. And let's say that a trucker drove an average speed of 60 miles per hour on his way out of town. He drove a trip 60 miles per hour for 1,200 miles. And then on the return trip, he had to go slower for whatever reason, and he drove only 50 miles per hour on the return trip. Of course, the return trip's the same number of miles, so it's also 1,200 miles. And the question is, what's the average speed for the whole trip? And at first glance, most of us would probably think, well, he drove 60 miles an hour all the way out there, and the exact same distance, he drove 50 miles an hour coming back, so you just average 60 and 50, and it's 55. And I want to tell you real quick, right off here, that's not the answer. The answer is not 55. He drove 60 miles an hour to go 1,200 miles, and then went 50 miles an hour again to go 1,200 miles. What's the average speed for the whole trip? Now, here's what we have to do to figure average speed. Average speed equals total distance over total time. For instance, if you and your family drove from here to California and you drove 3,000 miles and you really pushed it and you only stopped, you traded off drivers and this and that, and you just kept driving until you got there, but you of course had to make stops for meals and buy gas and this and that. But let's say it took you 60 hours to drive 3,000 miles. Well, your total distance was 3,000 miles. And even though you drove at very high speed sometimes on the interstates, probably going, especially out west, you can go faster, you can go 75 or more. And in other places, you got off the interstate, totally stopped, eat a meal or whatever. But your average speed for the entire 3,000 mile trip is just 3,000 miles divided by the 60 hours. And 3,000 divided by 60 comes to 50, which means the average speed for the entire 3,000 mile trip that took 60 hours was 50 miles per hour. Well, that's what we want to find for this situation, where it was 60 miles an hour for the first 1,200 miles and 50 miles an hour for the second 1,200 miles. And like I said, most of us, our instincts want to say, well, halfway in between 60 and 50 is 55. That's the average. Well, let's figure this out. We're going to have to use the D equals RT formula to figure out the time to drive out there and the time for the return trip driving back. So since D equals RT, we're going to take that formula and solve it for T. So using our algebra skills here, we look at D equals RT. To get that T by itself, we have to divide both sides by R. So we take T is equal to D over R. So the time to drive out to the 1,200 miles going out, it's distance divided by R. So the first time for driving out there, I'm going to call it T1, is 1,200 divided by 60. So that's 20 hours. And then the time it took to drive back, T2 we'll call it, was the distance divided by the speed. So that's 1,200 divided by 50. Well, 1200 divided by 50 is 24 hours. So I trust you see that the total time equals T1 plus T2, which equals 20 plus 24. The total time was 44 hours. So therefore, our average speed class for the whole trip, remember average speed is just total distance divided by total time, as 1,200 miles out there and 1,200 miles back, so 1,200 plus 1,200, rounded off, right? Exactly, 2,400 miles, divided by our total time of 44 hours. So you may already see this is not going to come out to be what it could have been, or what we thought perhaps it should be. 2,400 divided by 44 comes out to 54.54545 forever, going on for miles per hour. So that's to the nearest tenth of a mile per hour, it's 54.5 miles per hour. Now, yes, that's close to 55, but the point is it is not 55. And sometimes when you do these problems, you're going to come up with something much more different than what your first thoughts were. So that's how you do such a problem as that. So how do we do that again? We use the standard distance formula, D equals RT, and we had to solve it for T so that we could figure out what our time out there and our time on the return trip was, taking the distance both times at 1,200 miles, dividing by the speeds, 60 and 50 respectively, getting the two times of 20 and 24 hours. And once we had that, we had what we needed to solve the problem. My screen's frozen up again. I'm afraid having air server problems. I'm doing stuff, but, well, there it goes. Maybe it's just slow. Okay. All right. I'd like to go over one other type of word problem that's fairly common in algebra classes, and you're going to have at least one homework problem like this. The kind of problem where you have a mixture of things at, you can have all sorts of different mixtures of things at different prices or at different concentrations of some substance, and sort of different sorts of mixture problems. But let's do one with different prices. If we had, for instance, if we had a mixture of two types of nuts, and if we had say if we had peanuts that cost $2 a pound, and we had pecans, they cost $3 a pound. And then we had a mixture, a total of, say we had a total of 24 pounds in our mixture of peanuts and pecans, and then somehow we realized that somebody's already mixed this up for us, and they knew what proportion of peanuts and what proportion of pecans they put in it, so that they know how it came out, so that the mixture cost, or if you want to call it the average cost, of $2.60 per pound. And our job then, you've probably seen problems like this before, is to figure, well, how many pounds of peanuts are in the 24 pounds mixture and how many pounds of pecans are in the 24 pounds mixture. Knowing that peanuts cost $2 a pound, pecans $3 a pound, and the average cost of the total mixture of 24 pounds is $2.60 a pound. Well, how can we solve this? What we know is that the number of pounds of peanuts times the price per pound of peanuts plus the number of pounds of pecans times the price per pound of pecans has to equal the total number of pounds, 24 pounds, times the total average cost of $2.60, because the dollars of peanuts in the mixture plus the dollars of pecans in the mixture have to equal the total dollars. So if we set this up, if we for instance let the number of pounds of peanuts, if we call that P1, and the number of pounds of pecans, if we call that P2, then we can say P1 times, I'm just going to put the dollar amount in a round number, not with $.00. So the number of pounds of peanuts, P1, times the price per pound of peanuts, 2, plus the number of pounds of pecans, that's the P2 variable, times their price per pound, 3, of course in dollars, is equal to the total number of pounds, 24, times the mixture average cost of $2.60. So what does that mean? We have that equation, and we also have the equation that P1 plus P2 equals 24. So therefore P2 by itself is equal to 24 minus P1. So we can now plug in 24 minus P1, just plug that in for P2 right there. So let's rewrite the equation. P1 times 2 plus 24 minus P1 times 3 equals 24 times $2.60. Well, 24 times $2.60 is $62.40. Okay, so let's distribute this out now. We have now 2 times P1 plus 24 times 3, so that's plus 72, minus P1 times 3, so that's minus 3 P1, is equal to 62.40. All right, well, 2P1 minus 3P1, jumping over the 72, is just negative P1, and that's subtracting 72 from both sides, then that's 62.40 minus 72, and so that is negative 9 9.60. So what does that tell us? Multiply both sides by -1, and we get that P1 is equal to, let's just drop the 0, it's just 9.6 pounds of peanuts. It's not letting me do that. Maybe I've run out of room here. Oh no, still a little bit of room, good. And so remember that P2 is just 24 minus P1, so it's just 24 minus 9.6. So P2 is just 14.4 pounds of pecans. So we got our answer. We started off with a mixture of peanuts at $2 a pound and pecans at $3 a pound, with a grand total of 24 pounds of both of them mixed together at an average cost of $2.60 a pound. And we just went through an equation, set up an equation, and solved the equation, and we found out how much P1 was, 9.6 pounds. So there's 9.6 pounds of peanuts in the mix and 14.4 pounds of pecans in the mix. And we can do one other thing, class. We can now come back and check our answer. Not a bad idea in these kinds of problems. So let's check our answer. Let's do that in red. If our answer is correct, then 9.6 pounds of peanuts times $2 a pound plus 14.4 pounds of pecans at $3 a pound should give us our total mixture price of 24 pounds times $2.60 a pound, which was $62.40. Let's check and see. So we're going to do 9.6 times 2 plus 14.4 times 3, and we're looking to see, is that really going to equal $62.40? Well, here we go. 9.6 times 2 is 19.2 plus 14.4 times 3 is 43.2. And is that really equal to $62.40? Well, it's looking pretty promising, isn't it? 19.2 plus 43.2 is, yes, $62.40 does equal $62.40. That is in dollars and cents. Check, it works. So we just checked our answer that we did some good algebra, got a good answer. That's correct. And I just offer that to you as sort of a refresher. I know everybody's done problems like this before, but it might have been a while. As a refresher for you to enter into this section and begin working on these problems for the 2.1 homework. So I do hope this has been helpful. I'm personally thankful that the iPad did come back working again. It wasn't actually the iPad itself, it was the Air Server program that started messing up. But it came back and worked for us once again, cooperated, we might say. So there is a lesson for you on section 2.1 about solving equations and problem solving with linear equations. And ready to sign off this meeting. So again, I hope this has been helpful to you, and have a good rest of the day here.